Hello and welcome everybody to today's webinar on automatic Springback compensation in Stampack Express. And so we were very surprised and very pleased about the huge interest from all over the world to this topic. So my name is Luca. I'm a co-founder of Stampack GmbH and I'm responsible for the research and development team at Stampack GmbH. And today I will discuss with you a very interesting topic that is Springback compensation in Stampack Express. And I would like to give you more insights on our solution regarding Springback compensation. So what we will do today, before we start, I will introduce Stampack GmbH to those that maybe don't know about it. Then we should discuss shortly how we get the best Springback results, because Springback compensation can never be better than Springback itself. Afterwards, I will shortly introduce you in what is Springback compensation and what are the key requirements on a Springback compensation, because at the end of the day, everyone speaks about it and we have to make clear what we mean with Springback compensation. Next, we will discuss the key properties of Stampack's compensation algorithm, and we go into the very detail here. And afterwards, I make a live demonstration and then I will have some concluding remarks. And finally, at the very end of the webinar, you have the chance to ask questions, and we will do it in the following way: that you write them in the text in the chat, and then I will answer them one by one. And we try to make sure that we answer every question you have. Okay, let's go. So Stampack GmbH is founded in 2018 in Bietigheim in Germany, close to Stuttgart, and it grew to now 15 employees. There are 6 software developers in Spain, Barcelona, and nine people in sales, design and simulation in Germany. And so we do the technical stuff, the sales stuff, and the marketing stuff. And here in our office in Bietigheim, close to Stuttgart. And we could grow our company to now 132 software customers, which is a fantastic story for us, especially this year and the last year were amazing, with 40% growth last year and 30% growth this year. So we are in the middle of a fantastic story, and and I'm very happy to share more insights about Stampack with you. We started the company with a special mission. We wanted to make simulation software for tool designers. And this means Stampack Express should be a software that is sort of minimal, easy to use and straightforward. And it should use the language of the tool designers. So knowledge on finite element analysis and knowledge on material science should not be required when you use Stampack Express. Next, and this is a key point for us, and it's a key point for our success, Stampack Express provides fast computation and reliable results. And for those of you that are familiar with the simulation stuff, you know that fast computation and reliable results, that's a contradiction at the end of the day. And you need different technologies for fast computation, and you need a different technology for reliable result. And we will speak shortly about this within this webinar. And the last point, Stampack Express should be affordable for every tool shop and every engineering office. So at the end of the day, our vision is that every tool designer in the world has a simulation software installed on his workstation. What kind of processes are supported? Basically Stampack Express covers everything that runs on a press. So you can simulate progressive dies, transfer dies, hand insertion tools, and prototyping tools. And the processes we cover are classical stamping, but also deep drawing or ironing. And I'm quite excited that in the meantime, we added optimization algorithms like the Springback compensation we speak about today, or a trim optimization. Okay, now let's go. First part of today's agenda, how to get the best Springback results. I mean, that's a key question, and we could make an entire webinar on this topic. But I just want to give you a short overview um, uh, of Stampack solver and why is it different to other solvers on the market. So in Stampack, you can make a shell simulation, and shell simulation means that the sheet is discretized with triangular shell elements in the middle surface. And for us, it turns out that for thin sheets with larger radiuses, for example, for car panels, we have very good results in our shell simulation. But when the sheet gets thicker, so 2 millimeters and above, then when you hit the sheet with small radiuses, then the results in shell are not so good. But still, it's quite valuable because computation time is fast. So the benefit of shell simulation is basically, it's fast to run a simulation. You get a fast feedback, and you get a meaningful first impression for every kind of part. So this is what I mean with Stampack Express should have fast computation. On the contrary, in Stampack, you can also perform a solid simulation. And solid simulation is what I mean with reliable results. Solid simulation, you see here the sheet is covered with hexahedral elements all across the thickness, and you have a very physical contact on the top side and on the bottom side. And so stresses and strains along the thickness are considered. So you get high precision not only in the plane but also across the thickness. And this is very important in case of thick sheets and very important whenever we speak about compression. A quite nice benefit is that you can also see surface defects, and there is one key aspect that makes sure that very good Springback results are only possible in solid simulation, and this is what I try to explain you now. So due to the physical contact here on top side and on bottom side, you have a very physical compression behavior in solid simulation. And I have here now a very easy example. So an example that is not difficult at all. And in this example here in this corner, I think the sheet was 2 millimeter in the beginning, and we have a lot of thickening, I think. And at the end, when the press closes, then the thickening is compressed. And now we will take a look how shell simulation simulates the compression and how solid simulation simulates the compression. And then we will take a look on the Springback behavior of this part. So first let's take a look on the cross section in solid simulation. So you have here some thickening, and when the press closes, let's take a look. Then let's say by contact, the sheet is compressed, and in the middle of the process, it thickened more than 40%, but at the end of the day, it's fully compressed down. So we need a lot of force to compress to close the press here. And so this is in solid simulation. You see here what I mean with a very physical contact on top and bottom side. And okay, now we take a look on this very corner that we saw in the cross section some seconds before. And you see here 0.7 millimeter before the press close, shell simulation and solid simulation have quite comparable result. So a lot of thickening in this corner. And then when the press closes, yeah, the solid gets is compressed, yeah, and the shell is not. So the shell cannot show the compression behavior very well. And finally, okay, when the tool is closed, you have a huge difference in thickness here between shell and solid. So in solid, you're compressed almost to the initial gap of 2 millimeter, and in shell you still have about 40% thickening. And this effect has a huge effect on the springback afterwards, because you can imagine in solid, when you compress the sheet, yeah, you introduce a lot of strains along the thickness that afterwards stabilize the springback because you have more plasticity in the part. And then when we take a look on the springback displacement in Z direction, then you see, okay, the general behavior is quite comparable between shell simulation and solid simulation. But yeah, the magnitude is totally different. So we have here in shell 4 to 6 millimeter springback in this area. In solid, you have only 2.7 millimeter springback in this area. And yeah, you can imagine we want to speak about compensation now. And if you don't have a good result, yeah, if you are 2 millimeters off in the springback calculation, yeah, you can never compensate this very well. So the key takeaway should be at this point, to have excellent springback results, you need solid simulation, and the better your springback results are, the better your compensation is in the real world. I mean, this shell and solid is a deep topic, but we will push on now to springback compensation. And we start with a short explanation. What is springback compensation? And I try to explain it in a nutshell. So, I mean, our initial situation is typically like this. So I have here a nominal part, and typically in the first attempt, we form the part to the nominal part. We take out the part of the press, and it sort of jumps up. And so we get here a deviation vector, and the first approach to compensate the tools, the initial tools here on the right-hand side, they are typically at the same position as the nominal part. Yeah, but we compensate in the reverse direction to get the tools, to get better tool surfaces that let's say counteract the springback. So we sort of measure the deviation field and apply it in the other direction. So this is the first attempt. And in the second attempt, we will find that when we form the part to this shape, again, we have some jumping up, and we are we are closer to this blue, to the nominal blue, but still we have a deviation that is hopefully much smaller than it was before. And in the next attempt, we just apply this short deviation field, and we apply it again to the tools to get, let's say, the tool surfaces of the next iteration. And in this way, in a very iterative procedure, I try to improve my tool surfaces so that I'm at the end of the day very close to the nominal part, and that my part is in tolerance after springback. So what you have to know is before springback, I'm far away from the nominal, but after springback, as it is in real world, I should be in tolerance with the nominal part. And the takeaway of this short description in a nutshell should be that springback compensation does not reduce the springback at all. It counteracts springback, and it counteracts springback in the opposite way. And I have seen in many softwares the possibility to counteract, for example, with a factor of 1.1 or 1.2. And people claim that they have very good results with this, but it's not true because in some areas you need to compensate 1.1 time the first iteration. In some areas you need to compensate with 1.2 times the first deviation, and since we have these differences all over the sheet, we need to apply it in a very iterative way, so that we step by step locally improve the part until it's in tolerance. What we can learn also from this description is that we need some sort of measurement functionality. And I think you guys, you all know that measurement is a very, very deep topic, and you can spend years on measurement, and it makes a key difference how to measure springback and how to measure the deviation to the nominal part. But for sake of simplicity, we will not touch this deep topic in today's webinar. So if you have questions or remarks on this, please contact me after the webinar. Okay, quite clear is that springback compensation should modify also the tools, and it should modify the tools in such a way that we can perform the iterations one by one without manual, without touching the surfaces manually. So we want to not to touch the surfaces between the iteration, and this is what Stampack's compensation does. What are then the key properties of Stampack's compensation algorithm? So basically, Stampack's compensation algorithm takes 5 steps that are each very interesting and very deep. So the first one is what we call the tolerance check. So it's a measurement deviation to the nominal part. Then next, the tools are compensated to counteract the springback. So we take the deviation vector from the tolerance check, and we revert it on the tools, and we make sure that our algorithm is iteratively applicable, which means that we can rerun the simulation at any time with the new tools. And then there are some 3 specialties in our algorithm that are all very interesting. So, and we will discuss them in what follows. So the Stampack algorithm avoids undercut in vertical walls. It allows constraint areas on the tools, and it is length of line preserving. And I think we should speak about this in detail. So first, just that you get a feeling for how the measurement looks like in Stampack. So measurement means I import a nominal part and I perform a measurement against it, and I get here a color map, and I see exactly how far am I away from the nominal in each part of the sheet. And this is very convenient because typically I know from my drawings, from my CAD drawings, okay, here my tolerance is maybe 0.5, here it's 0.6, here is 0.1, and then I simply can take a look here on the color map, and then I can check the tolerance in a very easy way. Okay, I think it's quite clear what I mean with modify the tools, and that's why I jumped directly to the topic of undercut, or some people also know this under the wording negative angle. And in springback compensation, we typically have an issue whenever a vertical wall is involved. So in this part, we have a vertical wall all around the part. And I think you all know that when you have a vertical wall and you have to compensate this, it might be that you are in trouble because you fall into negative angle. But when you do this by hand, How can you know where you have negative angle? It's completely unclear. I mean, it could be here, it could be here. At the end of the day, we simply don't know. And that's why we integrated a functionality that we call remove undercut, and it's just a checkbox to activate. And with this, you can avoid the undercut. So this, what you see here, these are the tools after compensation. And we just take a look how the tools look like when we don't use the remove undercut functionality. I played in the video. So these are the tools and they are compensated. And okay, they are modified by the algorithm. And then when you compare it to the straight line here, you see that here the distance is lower than here. And the tools, because of Springback compensation, they fell into an undercut. And I think it's not a lot here. It's maybe 3% or 4%, but you cannot have a negative angle of 4%. It will totally destroy your part when you go on the press with this. And that's why we developed the functionality with remove undercut activated. And let's see how the compensation is done right now with this functionality. And you see here, we are within the whole compensation process, we are completely parallel to this line. So we do not fall into negative angle. And we can use these tool surfaces to run the simulation again, whereas this one cannot be used for another run. And this functionality or this tool setup does not really make sense for this kind of part. And in this setup, you would need a CAM tool, for example, to counteract the negative angle. So this is one of my favorites. This is, I think, my favorite button in our software. It's simply fantastic. Okay. What is also a key step in Springback compensation, that we cannot compensate all the surfaces, because in a part like this, you have here the blank holder area, and this is typically the draw-in area where the sheet is. At the beginning of the simulation, and you need a very smooth draw-in in the whole part. And if we would allow compensation here in this area, this surface would get a little wavy, I would say. And this is completely forbidden. So we need a tool that says, okay, in this area, compensation is not allowed at all. And in Stampack, it works in the following way. So we have here on the blank holder, we can say, okay, we don't allow compensation here. We constrain X, Y, and Z, and we fix it so that we don't have compensation at all. So this is mandatory for a good compensation of tools. And what is also very interesting, especially for symmetric parts, when I have a symmetric part, I will want to compensate on the left-hand side in the same way as on the right-hand side. And so that's why we also have these symmetry constraints, but they are less important than the fixing constraints that I need in almost every compensation procedure. And how does it work? I have here an example to explain it. So here on the left-hand side, we have an unconstrained area where we perform a normal compensation. And imagine here on the blank holder, we have the constraint, so we don't allow the compensation here. And I think it's immediately clear for you, that this cannot work, because when I have here compensation and I have here no compensation, there would be a very sharp border between these areas. And so I need a smoothing zone in between where I interpolate between the compensation area and the non-compensation area. And this is a smoothing zone. And we apply this smoothing zone automatically, so the user does not have to take care about it. It's simply done automatically, and it's very convenient to use because from our software point of view, the user does not really see this smoothing zone, but it exists. And when you think about it, it is clear that it has to exist. And the last thing, and that's also very special to Stampack's algorithm, this is what I call length of line preserving Springback compensation. And this can be explained very well in this top hat profile. So it's made of high strength steel, has a lot of Springback, and I think it's 20 millimeters here. And when you compensate this, this is the part after Springback. This is the compensated part. And when you compensate this in a naive way with a simple projection, like compensation tools in CAD softwares do it, then the length of this line here is increased by the projection. So you can imagine you have a nominal in between, and then it's simply projected downwards, and then the lines get longer. Yeah, but I mean, this is not working well, because imagine we make 4 iterations in our Springback compensation, and each time we add here 15 millimeters, so it does not make any sense. I mean, I know that this is a part especially designed to show this effect, but even if you just compensate 5 millimeters, and in each iteration you add 0.5 millimeters, then after 4 iterations you added 2 millimeters of length on the lines, and then you get a completely different part, and you can never be in tolerance. So it's a key feature of Stampack's algorithm that we preserve the length of line. So here the yellow part, this is the Stampack compensation. It's much shorter than the compensation done in our CAD system, and the length of the line is the same as in the original. And here in another example, I think here we had 15 millimeter Springback. And also here, I liked a lot to see that our compensation preserves the length of this line. So I'm very pleased with this result. Just to give you some examples. So we applied, so our compensation algorithm is now on the market for I think 1.5 years. And I would simply like to share some customer experience with you. So where you just see the progress on how quick the compensation is converging. So we have here a version of the top hat profile we spoke about. So it's 12.5 millimeter Springback, and already in the first loop we could get a deviation of 0.59 to the nominal and 0.79 to the nominal here in the other corner. So in this kind of very easy part, we have a very fast converging behavior, and you don't need many iterations. In more real-world examples, it's a little different. So this is a B pillar, for example. In the B, I think we had a maximum deviation of 4.48 here in the corner, and then you see how the algorithm works. So here it sort of overcompensated in the other direction. So we were above the part. Now we are here below the part, and only in the second iteration, then we jump now very close to the part as it should be. And this is also something typical, that, let's say, the convergence is a little unstable, in the sense that it's somehow overcompensating, and then and just step by step you come back and get better. But I think after 2 loops that this is still perfectly all right. And another example that I really like, and this is an example of the company Pengfei in China. here they had 2.8 millimeter springback on this part, but the part is special in the sense that it looks extremely easy. So if you give this to anybody, maybe they will say, okay, you don't have to use simulation software at all. But they had very strict tolerances on it. So I think the tolerance was 0 to 3 millimeter. And when you have this kind of strict tolerances, then you have to go for it. And then the easy part gets very, very difficult. And here you can see how our compensation algorithm converged to the final goal. So here in the corner, yeah, it went down quite step by step. And here in the middle, it sort of overcompensated in the first attempt and then started to converge. So you see here also that the behavior is locally different. So here we have a very smooth transition, and here it's a little wavy. So, but this is very typical for a compensation, and with this you see that you cannot work without an iterative compensation approach. Okay, that's it for the moment. I think we should now switch to Stampack, to the software, and I show you how to define a springback compensation, and then we can take a look on a result. And afterwards, I make some concluding remarks. Okay. So I prepared here a simulation for you, and I don't want to define a simulation with you. So we start to take a look on the process I have here, and then so it's already calculated. The simulation is already calculated. Yeah, it's forming, cutting, springback, and I introduce you in the process, and then we check how we can define the compensation. So let's load it. So this is a very typical drawing part. I think it's 500 millimeters. I think it's a part that is in the exhaust system at the end. And so just that you get a feeling how the part is formed, is a classical drawing. Yeah, you see here the blank holder area, and now you see here this is flat, and it has to remain flat also afterwards, after we compensated the tools, just to guarantee the optimal draw-in behavior of the material. And so step by step, the part is formed. Then we have a cutting, and then we have a springback, and okay. And so you have a lot of possibilities here in Stampack, and I think you guys, you all know about it. You can check whether the part is feasible or not. You can check how the thickness behavior is. You can check the wrinkling, but we will not do this today. We just make one thing, and that is we have here imported a reference, and the part is measured against the reference. So I think here it's the top side. It's measured against the top side of the tool, and with this color map, with this distance to target or with this tolerance check, you can see the deviations after springback. And you see here that here we are 2.2 millimeters off, and maybe in each point in the mesh you can visualize the distance to the nominal, and it's clear that we have to do something at this point. I think the tolerance here in this area was maybe 0.5, and I think here more outside it was 0.75 or something like this. But definitely we have to counteract the springback. And now we will take a look how to do this. So I go back to the pre-process, and we are here in the springback operation. So here's the forming, cutting, springback, and in the springback What is already defined is our tolerance check, that is the compare to target functionality. And what we are going to do now is we use here the Springback compensation. And to do it, I have to import the tools that I want to compensate. So we have here the top, the bottom, and the blank holder, and they are, in this case, they are imported as parasolid files. So the ending was x/t, but equally you can import CATIA, NX, Creo, STL, IGES, STEP. So you have the full freedom here. And okay, I import them. And I have them now here in the so-called warehouse. And warehouse is a location for geometries that are not yet assigned. And I pick them. So, and then let's say I add them to the compensation surfaces. And I have three possibilities. So I can add a compensation surface. In this area, this surface is compensated as it is. I can add a constraint surface. So constraint surface is what we will do with a blank holder. We will take a look on it in a second. And we can import also cutting lines. And this is because in some processes, we also have to arrange the cutting line, because when we compensate differently and we have, for example, a laser cutting, then we also have to change the cutting a little. I think that's quite clear. So we take the geometry and we add the top part as a normal compensation surface because it should be compensated. We take the bottom part as a compensation surface. And now we know that we do not want to compensate in the blank holder area. And so I add it as constraint surface. And on this constraint surface, I get some option. So I can constrain in this blank holder area and fix the part on it. And I can do this in each space direction. And what I could also do, and I'm not going to do it, I can say, okay, within this symmetry plane, you compensate the part in a symmetric way, which means if the symmetry line would be here in the middle, the left-hand side and the right-hand side would be compensated in the same way. Yeah, and that's it. And now we can, maybe one more comment, I forgot about it. What you see here, and this is automatically activated, the checkbox remove undercut. And when it's activated, then the undercut is removed automatically. When it's not activated, then the tools are compensated in a way that they can fall into undercut later on. So typically, whenever people make drawing parts, it's very good to have it activated. And if people make bending parts, typically they counteract Springback with some cam tool, and then they don't activate this. Okay, that's it so far. And now we have to press on calculate. We just have to recalculate the Springback operation and the compensation. And I think I don't want to do this right now because I calculated it already for you. Let's take a look. The compensation time was, 1 minute and 24 seconds for the compensation. The total simulation time in the solid, this was simulated in solid, was 21 minutes, just to give you some insights. And I load this now the compensation. And then we can take a look on what happened within this compensation. And just to explain it, I make a cross section. And what you see here is, zoom out a little. So before Springback, the tools and the part are in the same, they are in the same position. And what will happen now is the part is going out because of Springback, and then the tools are compensated in the reverse direction, and they are compensated in such a way that we don't fall into undercut. So this is how it works. So you see the compensation algorithm is making this radius a little larger, but what you can also see very well here is that the tool gap remains constant within the compensation procedure, which means, and this is mandatory, that you can restart the simulation again and get a very good result once more. And this is how it works. And now in this way, I generated new tool surfaces. And I can take now this new tool surface and restart this procedure. And then step by step, in an iterative way, I get a part that is in tolerance. And in this case, it took 3 iterations. And I want to show you now how the distance to the nominal is now. So we have here again our distance to the nominal functionality, and now we can see, okay, the maximum deviation is 0.64, the minimal minus 0.67, so it converged in 3 iterations. And what we see here, that we are quite close here in the center, and just here below, yeah, we still have some deviations, and this is because of the remove undercut, because I cannot compensate exactly in the way I want to do it, because I have to ensure that the vertical wall remains vertical. But still, if you remember, before the compensation, we were here 2.7 millimeters away from the target. Now we are 0.4 millimeters away from the target, and this is simply fantastic. And now you can export these new generated tools to CAD, and you can continue to work from the CAD side. So this is how it works. So that's all about the real world example. And what else is interesting? I jump back to the position where we were. So what else is interesting? So besides Springback compensation, you have several possibilities in Stampack. So I want to give you a summary of all the possibilities you have. So there is the basic module to define the simulation and to take a look on the results. So this is what we have seen. And in the basic, you can calculate the shell, you can calculate the solid, and you can calculate the Springback. And then there is a module called Measure and Optimize, where you can make the Springback compensation that we have seen right now, where you can make the trim line development with the trim optimizer, and where you can use the tolerance check. So that is the measurement against the nominal. Then there is a module called Import to Mesh, where you can import native CAD data. And 2 things are very interesting. So if you are in Stampack subscription, the floating is included. And also very interesting is the free viewer. So we have many customers that have maybe 1 license of Stampack Express, and they have many viewers in the company. And so you can share simulation results with your colleagues in a free way, and they can take a look and learn from the simulations without the need of another license. What's I think also interesting, and this is for when we speak about Springback, it's a key topic because Springback results are highly influenced by the quality of the material data, and we have about 570 material cards inside Stampack, and we work together with the suppliers Bilstein, Salzgitter, Tata Steel, voestalpine, and ThyssenKrupp. And they bring their materials directly inside the software, also with the most modern anisotropic models. And so it helps us to predict the Springback very well, and I'm very happy that these companies worked with us together. Our materials are for all in all for steel, aluminium, stainless. So what we have seen in the simulation right now, this was a stainless IC304, and we also have a database for copper and brass. So we have a good range of materials and also some Inconels. Which companies use Stampack Express? So I don't want to show all the 132 companies, but just that you get a feeling. So Magna, this is Cosma Die Technology in Detroit, is using Stampack, especially for thick sheets. So they work a lot with our solid simulation. Allgeier Automotive, big supplier in Germany. I think Daico, Denso in Spain. And for example, Sonaca and Bombardier are more from aerospace industry. And maybe you also know Kirchhoff. That is that is a global automotive supplier. Or Samsung is using Stampack Express for household parts, so completely different topic than automotive, but also quite challenging. And what you may maybe also know are some Japanese companies, Toshiba, Fuji. They are more in the business of electrical connectors. Okay, that's it from my side for the moment. Thanks a lot for your attention. If you want to see more examples, please visit our webpage and go to the example sections. So here on each box, you get a wonderful video, and you can go there and you get a feeling for the range of parts we cover. And in these videos, we typically explain a certain aspect. Please also follow us on LinkedIn. Once a month, we give we give an update, and we typically do this by adding a video. In this case, the last video was completely different topic than today's Springback compensation. It was about tolerances in stamping of copper, also a wonderful topic. And in this video is explained how Stampack helps to produce this kind of part. But I think next month we will provide a video on forming of embossed sheets, and so the topic is changing frequently, and for everybody we have something interesting. If you have feedback, you are always welcome. Please contact me. So this is my email address, or phone me, and then we can get into discussion.